For years, deep learning struggled with sequential data. Recurrent neural networks, RNNs, processed words one after another, perfect for understanding language, but agonizingly slow to train.
Right, because each step depends on the previous one. You can't really speed it up. We talked about that in earlier cases, about how that sequential dependency limits things.
Exactly. This paper from 2017, Attention is All You Need, challenged that dominant approach. It starts by saying, the dominant sequence transduction models are based on complex recurrent or convolutional neural networks.
Okay, so the landscape at the time was RNNs and CNNs for sequence tasks. What did they propose to change that?
They proposed a radical shift. They state, we propose a new simple network architecture, the transformer, based solely on attention mechanisms, dispensing with recurrence and convolutions entirely.
Solely on attention? That's a strong claim. We've covered attention in hashtag TCM153002 as a way to weigh relationships, but removing recurrence completely seems bold.
It was bold and transformative. The core idea was to make sequence processing more parallelizable and requiring significantly less time to train by focusing on relationships rather than order.
So if you don't have to wait for the previous step, you can process everything at once. That's the parallelization benefit we saw in hashtags TCM213002.
Precisely. The title, Attention is All You Need, captures this radical simplification. It's not just that attention is useful, it's that it can replace the traditional core components.
So the pitfall here might be thinking attention is just an add-on. This paper argues it's the main event, the entire engine.
And they proved it with results. The paper highlights, experiments on 2 machine translation tasks show these models to be superior in quality. They didn't just propose, they delivered.
Like English to German and English to French? Those are big benchmarks. What kind of games did they see?
Significant. For English to German, our model achieves 28.4 BLE EU on the WMT 2014 English to German translation task, improving over the existing best results, including ensembles by over 2 BLE EU.
Over 2 blue points is a huge jump in machine translation. To put it in perspective, a 1-point blue increase is often considered significant and hard-won. And faster training too. That's a clear win for this new architecture.
This paper fundamentally reshaped how we think about sequence modeling. It showed that attention could be the universal mechanism. But how does it actually do that? Let's trace the intuition.
All right, from the bold claim to the underlying mechanics.
Where do we begin unpacking the transformer itself?
Let's use this fantastic illustration to build our mental model. Imagine the transformer as a translator. In a machine translation application, it would take a sentence in one language and output its translation in another.
Okay, that's the classic sequence-to-sequence problem. Input sequence, output sequence. How does the transformer break that down internally?
Popping it open, we find 2 main parts, an encoding component, a decoding component, and connections between them. Think of it as a factory with 2 distinct halves. The encoder is like the raw material processing plant, and the decoder is the assembly line for the final product. Where this analogy breaks is that these halves aren't entirely separate. They communicate in complex ways, especially through attention.
The encoder processes the input sentence, and the decoder generates the output, like many seek-to-seek models we've discussed before.
Precisely, but with a twist. The paper describes the encoding component is a stack of encoders. They use 6 in the original paper, but it's really about depth of processing.
So it's not just one encoder, but layers of them, each refining the representation. Does this mean the same for the decoder?
Yes, the decoder is a stack too. The key is that the encoders are all identical in structure, yet they do not share weights. Each one is broken down into two sublayers.
2 sublayers within each encoder? What are those and how do they differ from traditional RNN or CNN layers?
The first is a self-attention layer, a layer that helps the encoder look at other words in the input sentence as it encodes a specific word. Imagine a word consulting all its neighbors to understand itself better, like a detective gathering witness statements. The analogy holds in that it's about relational context, but it breaks because consulting here is a parallel mathematical operation, not a sequential conscious deliberation.
This is the core of what we discussed in TCM 153002. Self-attention allows each part of the input to dynamically weigh the importance of all other parts to its own representation.
Then, the outputs of the self-attention layer are fed to a feed-forward neural network. This second layer processes the enriched information from self-attention.
So self-attention gathers context, then the feed-forward network processes that context independently for each position?
Crucially, this is where the parallelization comes in. The feed-forward layer does not have those dependencies, thus the various paths can be executed in parallel.
That's a key distinction. Self-attention creates dependencies to gather context, but the feed-forward layer then allows for independent, parallel processing of each token's enriched representation.
However, this parallel processing comes with a challenge. Since the transformer dispenses with recurrence, it has no inherent sense of word order. The original paper's breakthrough relied on throwing away sequence in favor of parallel processing, but sequences have order.
So if the dog bit the man and the man bit the dog get the same words but no order, the meaning is lost. How does a transformer fix that without bringing back recurrence?
It uses positional encodings. These are numerical vectors added to the word embeddings at the very beginning of the process that inject information about the position of each word in the sequence. These encodings are learned or fixed patterns that the model can then use to understand relative and absolute positions.
So it explicitly tells the model this is the first word, this is the second word, etc., allowing it to combine the relational context from attention with the sequential context from the encodings. That makes sense.
This encoder-decoder structure with self-attention inside is the architectural backbone. Now let's dig into how that self-attention truly works with its query, key, and value vectors.
Yes, we've seen the high level. Now let's see the detailed mechanism that enables this dynamic contextual understanding.
Consider the sentence, "The animal didn't cross the street because it was too tired." When the model is processing the word it, self-attention allows it to associate it with animal.
That's the core task of understanding pronoun reference. It needs to know which word it refers to, not just its dictionary definition.
To achieve this, the first step in calculating self-attention is to create 3 vectors from each of the encoder's input vectors. For each word, we project its embedding into 3 different spaces. These are the query, key, and value vectors we introduced briefly before.
What roles do they play in finding associations?
Exactly. For every word, we get a unique query, key, and value projection. We end up creating a query, a key, and a value projection of each word in the input sentence.
So 3 different vector representations for each word.
how do they interact to establish meaning?
The next step, calculate a score. If we're processing thinking, we score each word of the input sentence against this word. Think of the query as a question you're asking, and keys as the index tags or labels of other pieces of information. A strong match, high dot product, means that piece of information is relevant to your question. The analogy works well for finding relevance, but it breaks in that asking and offering are simultaneous vector comparisons, not symbolic language acts.
So the query for thinking asks, how relevant is every other word to me? And each word's key answers that question.
Precisely. The score is determined by the dot product of the query vector with the key vector of the respective word we're scoring. A high dot product means high similarity, high relevance.
So for its query vector would be dotted with the key vector for animal and the key vector for street. Whichever dot product is higher indicates stronger relevance.
Once scores are calculated, the third and fourth steps are to divide the scores by 8. This 8 is the square root of the dimension of our key vectors, which is 64 in the original paper. And this scaling step is crucial for making the gradients more stable during training, preventing the dot products from becoming too large. After scaling, we then pass the result through a softmax operation.
This normalizes them so they sum to 1, effectively saying how much attention each word gets as a percentage. It makes the attention weights clear.
And finally, multiply each value vector by the softmax score. The intuition here is to keep intact the values of the words we want to focus on and drown out irrelevant words. After this, we sum all these weighted value vectors to produce the final output for that specific word's position.
So the query finds relevance, the key provides the context to be found, the value provides the actual information, and then we combine all the relevant information, weighted by their importance, into a new context-aware representation for that single word. That's the output of self-attention.
This dynamic interaction is powerful, but it comes at a cost. The self-attention mechanism involves calculating these scores between every query and every key in the sequence. If you have a sequence of length n, that's n squared calculations for the attention weights.
N squared?
So if my sequence doubles in length, the computation for attention quadruples? That seems like a major bottleneck for really long sequences, like entire books or high-resolution images.
Precisely. This quadratic complexity is one of the honest limits of the original transformer architecture. But its core idea of sequence processing via attention is so powerful, it is generalized far beyond language.
So we've broken down the transformer for language, but you mentioned earlier it's universal across modalities. How does this same architecture apply to something completely different, like images?
That's the beauty of its design. The core insight is that if you can represent any data as a sequence, the transformer can process it. The most famous example in vision is the vision transformer, or VIT.
Instead of words, imagine an image. How do you turn a 2D grid of pixels into a 1D sequence for a transformer?
We don't feed the raw pixels. Instead, we divide the image into a grid of small, non-overlapping patches, like tiles on a mosaic. Each image patch is then flattened into a vector, creating a sequence of these visual tokens.
So each patch is like a word in a sentence, giving the transformer its input sequence.
Precisely. Just like with words, each visual token needs to be embedded into a high-dimensional vector space. And crucially, because we've turned a 2D image into a flat sequence, we still need to tell the transformer where each patch came from, its relative position. So positional encodings are added to these image patch embeddings too.
So it's the exact same trick?
turn everything into a sequence, add position information, and then feed it to the same transformer encoder block?
Exactly. Once you have that sequence of position-encoded patch embeddings, you feed it directly into the standard transformer encoder. The transformer, based solely on attention mechanisms dispensing with recurrence and convolutions entirely, can now process visual information just as it processes text.
So the all you need isn't just about language, it's about sequence processing in general. It just needs to be given a sequence, regardless of whether that sequence originated from words or image patches or anything else.
And it worked remarkably well. VIT showed that transformers could achieve state-of-the-art results in image classification, often outperforming traditional convolutional neural networks, demonstrating that the architecture generalizes well to other tasks.
That's truly groundbreaking. Taking a model designed for text and applying it to images with such success, showing a fundamental universality.
It cemented the idea that attention mechanisms provide a flexible and powerful way to model relationships within any sequential data, regardless of its original modality. This approach has since expanded to audio, video, and even molecular structures.
So the transformer taught us that the world is just one big sequence, and attention is how we make sense of it, no matter the data.